So in this video, we're going to talk about sinking funds. So what is a sinking fund? Well, a sinking fund is a type of annuity in which money is saved to reach a fixed future value, often used to pay off a future debt. So let's take a look at an example of a sinking fund. In example 3, we have a new parent wishes to save $50,000 in a sinking fund for their child's college. The account pays 4% interest compounded quarterly, and compounded quarterly means every 3 months, and payments will be made quarterly every 3 months for 18 years. What should be the quarterly payments? So again, what we're doing here is we're saving for a future value. So we want the value of this annuity to be $50,000 18 years in the future so that we'll have the money to send the child to college. That's the purpose of this. So we want to know, what does the payment need to be? How much money do they need to save each quarter and put into this sinking fund so that it will be worth $50,000 18 years from now? Well, this is really just an annuity problem, but the difference is, in this case, we know what we want the future value to be. So we know what A should be in our annuity formula. We also know what the interest rate is. We know how often we're compounding, and so on. So we're looking for the future value. So we're going to use our same annuity formula. A equals R times, parentheses, 1 plus R over M raised to the n power minus 1 over R over M, close the parentheses. So we're using the same annuity formula that gives us the future value of the annuity, but what we're going to do in this particular case is we're going to use that to figure out what our quarterly payment needs to be. So if I figure out what it is that I know, again, I want the future value to be $50,000. So I know what A needs to be, what the future value needs to be. What I don't know is what the quarterly payment needs to be. Now I know my interest rate is 4%, so that is 0.04. I know that we're compounding quarterly. Quarterly means every 3 months, so that's 4 times per year, so M is equal to 4. Now I also know that I'm doing this for 18 years, so the time is 18 years, so the number of times that we're going to compound the interest is going to be M times T, so that's going to be 4 times 18 in this case, which is 72. So we're going to compound the interest 72 different times. That's N in our formula. So filling in what I know, I have $50,000 is equal to R, which I don't know, that's what I'm trying to figure out, times 1 plus 0.04 divided by 4, but again, because our interest rate's 4% and we're compounding quarterly, so that means 4 times per year. Now that gets raised to the 72 power minus 1, and then that gets divided by 0.04 divided by 4. So I have $50,000. That's going to equal R times, I want to clean this up. Well, 0.04 divided by 4 will be 0.01. So 0.04 divided by 4 is 0.01, and 1 plus 0.01 is 1.01. So here I have 1.01 that's being raised to the 72 power, minus 1. And again, 0.04 divided by 4 is 0.01. So I have this particular formula. Now, I want to figure out what this is. Well, if I take 1.01 raised to the 72 power minus 1 and divide that by 0.01. So again, I'm I'm doing this calculation right here. Now to do this calculation on my calculator, I have to put the numerator in parentheses. So that's why I have parenthesis 1.01 raised to the 72 power minus 1, close the parentheses because I'm dividing all of that by 0.01. And that is 104.7099312. So I have $50,000 equals R times 104.7099312. I'm not rounding that because I don't want to round until the end so that rounding doesn't cause error. So 50,000 equals R times that 104.099312. To solve for R, I'm just going to divide both sides by 104.7099312. So 104.7099312. So if I take 50,000 divided by 104.7099312, that is 477.5096 and so on. So now I'm going to round, so that would be 51 cents. So R is going to equal $477.51. So these parents, if they want to end up having $50,000 18 years in the future, they're going to need to deposit $477.51 each quarter for the next 18 years. So for every 3 months, they're going to make a $477.51 payment, and if they do that, then at the end of the 18 years, they will have $50,000 in their sinking fund. Let's take a look at one final example for this section. Look at example 4 here. Another example of a sinking fund. Anna will retire when she has saved up $2 million. She plans to put $1,000 each month into an ordinary annuity that pays an annual interest rate of 6% compounded monthly. In how many years will Anna be able to retire? So this is the same kind of problem that we just did in example 3, except in this particular case, what we're looking for is the time. How many years is it going to take Anna to be able to retire? If she can't retire until she has $2 million, and she's going to be reaching that $2 million by putting $1,000 a month into an ordinary annuity. So again, we're going to use our same formula. A equals R times 1 plus R over M raised to the N minus 1 over R over M. So again, Anna wants the future value to be $2 million. Her payment is going to be $1,000. Her interest rate is 6%, and she's compounding monthly. What we don't know is the time. So again, just writing down what I know, A is $2 million. R is $1,000. The interest rate is 6%, or 0.06, and we're compounding monthly, so M equals 12. What we're looking for is time. We don't know what that is, but we do know that N is going to equal M times T, so in this case that is 12 times T. We just don't know what T is. So how many years from now will Anna be able to retire if this is her plan? Well, let's fill in what we know and solve for T. So $2 million is equal to $1,000 times 1 plus 0.06 divided by 12 raised to the 12t power, that's what n is, minus 1. I missed my parenthesis there. And that is over 0.06 divided by 12. And so I'm needing to solve for t. Well, let's clean this up a little bit. So my $2 million is equal to $1,000 times, clean this up in here. So 0.06 divided by 12 is 0.005, and 0.005 plus 1 is 1.005. So I have 1.005. Again, that's what 1 plus 0.06 divided by 12 is, and that's raised to the 12t power minus 1. And again, 0.06 divided by 12 is 0.005 right here. Well, how can I clean this up and solve for t? Well, notice that t is an exponent, so I'm going to have to eventually get that down from being an exponent, and to do that is going to require logarithms. But before I can do that, I need to get rid of the 1,000, I need to get rid of the 0.05, I need to get rid of the minus 1. So I'm going to start by dividing both sides by $1,000. You could do this different ways, but that's where I'm starting. Well, bring in my calculator. If you take 2 million and divide by 1,000, that's 2,000. And notice the dollars divides out. So I have 2,000 is equal to 1.005 raised to the 12t power minus 1 over 0.005. So in other words, dividing both sides by 1,000 got rid of the 1,000 for me off of the right-hand side. Now I can get rid of the 0.005 if I multiply both sides by 0.005. So I'm multiplying both sides by 0.005. So if I take 2,000 times 0.005, that is 10. So on the left side here I have 10. And on the right-hand side that divides out. And so I'm left with 1.005 raised to the 12t power minus 1. So again, I'm trying to solve for t. So if I add 1 to both sides, well, 10 plus 1 is 11, and that's going to equal 1.005 to the 12t power. And I'm going to bring that over here just to have more room, and I'm going to flip it around. So I'm going to write this as 1.005 to the 12t power equals 11. So now I just have this 1.005 to the 12t power equals 11. I need to get that t down from being in a power, so I can do that by taking the log of both sides. So the log of 1.005 to the 12t power equals the log of 11. So I can now pull that 12t down. So 12t times the log of 1.005 equals the log of 11. Now remember, the log of 11 is just a weird number. The log of 1.005 is just a weird number. And 12 is just a number. So if I will divide both sides by 12 times the log of 1.005, on the left-hand side, dividing both sides by 12 gets rid of the 12. Dividing both sides by that weird number, log of 1.001, leaves me with just t. On the right-hand side, I have the log of 11 divided by 12 times the log of 1.005. Now, I do have to be careful how I type that in my calculator. I'm going to do the log of 11, close the parentheses, divided by, now I need to put this in parentheses, so I'm going to do 12 times the log of 1.005, close the parenthesis for the logarithm, close the parenthesis for the denominator. So I have to put that denominator in parentheses so that the calculator will do that calculation first before dividing log of 11 by that. If I do that, I get 40.06. So this is approximately 40.06. So about 40 years. So if Anna puts $1,000 per month into this annuity, at the end of 40 years, she'll have $2 million to retire with. I do want to point out really quickly that if you're uncomfortable typing this in the way that I did, we could have figured out what the log of 11 is, and we could have figured out what 12 times the log of 1.005 is. So like at this step, when I had 12t times the log of 1.005 equals the log of 11. So when I had that, I could have figured out that 12 times the log of 1.005, I could figure out that that is 0.025992741. So what I really have here is t times 0.025992741. And I could figure out that the log of 11 is 1.0413928685. So this equals 1.041392685. And so then I could have divided both sides by 0.025992741. So if I divide by that 0.025992741, then I would get t equals whatever that is. So if I take 1.041392685 and divide by 0.025992741, that gives me the 40.06 years. So I could have done that. Just be careful not to round, because if you round, that's going to cause problems. So either way, we learned that it takes Anna about 40 years to retire. That completes this section. You should now be able to do the section homework.